Hi, this is part 2 of my video series on LOL diagrams and solving for unknowns in energy. So last part I did part 1 that was qualitative LOL diagrams. Now we're going to move on and do quantitative. That means we're going to have to think about equations and do a little bit of math. Hey, math. So I have a new scenario here. It says a 50-gram rock, so we have a mass, is dropped towards the earth. It starts off at a height of 10 and then falls to a height of 2. It is going 12.5 meters per second in the second snapshot. Okay, so let's digest first what forms of energy are present. So it says we have height in 2 different scenarios. So that means we are going to have gravitational potential energy. We're going to have that in both initial and final scenario. I want to keep that in mind. And then it says that in the second snapshot, it is moving. So that means that we are going to have kinetic energy. I meant to say in this one that there is going to be no friction. I have no friction this time. So we know that the kinetic energy is moving, second snapshot. There's no springs, nothing's being stretched or compressed, so there's no spring energy. And since there's no friction, there is no thermal energy. Great. Now we just need some values. So let's do some math first. So I want an initial gravitational potential energy, so UG. I know that UG is equal to mass times gravity times height. I'm going to say height 1 because this is our initial scenario. So let's start plugging in some numbers. So UG is equal to our mass, which is 50 grams, which is 0.05 kilograms. We know gravity is 9.8 meters per second. And then we have our height 1, which is our height in our initial scenario. Okay. Our initial scenario has a height of 10, so we have 10 meters. Great. So that means UG in our initial snapshot is going to be equal to 4.9 joules. Okay. Now we need a final UG. Same formula, but now we have a second height that we have to account for. So UG is equal to mgh2. So UG, potential energy, is that same mass, 0.05 kilograms times 9.8 meters per second. But now instead of 10 meters, it says 2 meters. 2 meters. So that is going to give us a UG equal to 0.98 joules. Check it out. Those two values don't equal each other. Since we go ahead and since we know our values, let's go ahead and put them on our LOL diagram. So I'm just going to open it up. And this time I need to provide some scales. So I know that I have to be able to get up to 4.9 joules. So we'll aim for 5. I'm actually going to, I think, can I shrink everything? Yes. Kind of messes this up, but we'll just. There we go. Give myself a little bit more room here. Great. Because I want to be able to get up to 5. So I know that the bottom part of my graph is 0, so I just need to say 1, 2, 3, 4, 5, and this is going to be a measurement of energy in joules. Okay, now I'm going to rotate this so that it's the correct direction. I know that's 0, so I'm just going to add some spaces until it all fits. Pretty even. Okay, and I'm just going to copy and paste this onto my other LOL diagram so that they have the same amount of scale. Cool. So our first energy form was that height initial, which was 4.9 joules. So I'm going to add a bar under UG in my initial scenario, and I'm going to go almost to 5. And then I'm going to add a text box underneath, and I'm going to say that this is 4.9 joules. Here we go. The label. We said that there was no kinetic energy in that first snapshot, so I am going to get a little X here. Right there. And paste. I also know that there's no spring energy because it's just being dropped, nothing's being stretched or compressed. We need to go ahead and put what objects are in our system. So we have the rock and the earth, and that's it. Nothing else. No other objects. Okay. We know what our gravitational potential energy is already for our second snapshot. It is that 0.98 joules. So I'm going to copy and paste my bar so they have the same width. I'm going to put it over here, but then I'm going to shrink my bar down because this needs to be 0.98. I need to go all the way down to below 1. Okay, so now all of this energy, only some of it has stayed as gravitational potential energy. It has to have gone someplace. It's gone into our kinetic energy. It's gone into that velocity. So I'm just going to add a label underneath so I know exactly what that value was. 0.98 joules. I like to have a space between my number and my unit. Okay. Great. That looks good. So now I need to calculate for that kinetic energy so I can put in that last bar. So kinetic energy. Our formula for kinetic energy is K equals 1/2 mv squared. We already have all these values because this is just a simple problem to start calculating some stuff. So that K is 1/2 times the mass, which is 0.05 kilograms, times our velocity squared. Don't forget to square it, 12.5 meters per second. And then we got to remember to square that. So if I plug that into the calculator, that is going to be a K value of 3.92 joules. Great. We've got some values now. Let's double check to make sure that energy was conserved. So I have my initial snapshot, I have 4.9 joules. And then on my final snapshot, because this kinetic energy is only in the final, I have 3.92 and 0.98. Let's add that up to make sure that it all adds up. So 0.98 plus 3.92. Yep, that equals 4.8. Oops, I messed up. 0.98. 0.98 plus 3.92. Yep, 4.9. It all. I'm not going to do this. You can't even read it. That adds up to 4.9 joules. So definitely no energy has been converted to heat. Nothing's been lost. We can still say friction is negligible. Let's add our last bar. We need to add that 3.9 joules for our kinetic energy. So I'm just going to copy paste that bar over again and then just adjust the height as I need it. So 3.92 needs to be below 4. Right. Actually, let's just make sure that all the bars add up. So got one here, got one here. So it looks like we can do some adjusting. Trying to make it a little more exact. There we go. Now they add up. So definitely, see, I think that makes it too big. I think it's got to be this way. Yeah, that's better. It's a little rough because I don't have an exact scale here, but really your bars should just add up and look really nice. Okay. And we need our label. Almost forgot our label. which is going to be 3.92 joules. Great. It doesn't have to be perfect, it just has to be readable. Okay, great. Hopefully this has been helpful and you can kind of see how you can use those LOL diagrams to plan and also like how to use some of those basic equations. Part 3, we're going to put it all together in a little bit more of an organic problem, and that's going to be much more helpful. So I will see you guys in part 3.